So you see what I see, right? Okay. All right. I'm trying to find that. Thank you very much. Sorry for the little technical problem. I would like to thank the organizers for this great meeting. Indeed, I have a very, very minor part of the organization, but I would like to thank to Herbie, Sarah, and Kirsten for all the amazing work that they did, so they bring all of us here. And I would like to thank also all the speakers before me, because they did amazing exoplanet talks, and I don't have to introduce anything now. I think you all know about exoplanets. So I'll just move to my favorite topic. As an exoplanet hunter, my primary focus is always been to detect multiplanetary systems and to characterize their orbits. Okay, so I would like to tell you more about that, and I would like to introduce you what kind of problems we have. I would provide a solution, and I would like to tell you more about our plans in future, how we try to tackle these kind of dynamical problems in multiplanetary systems. And if we have time, and I hope we will have time, I would like to present a new multiplanetary system that we just discovered like a few days ago. Okay, so why I think that multiplanetary systems are amazing? Not just because we're detecting more than one planet in a system. It's also because their dynamical architecture is actually a fossil record of the planet formation and evolution. So if we were able to get the dynamic architecture of the multiplanetary systems now, we can reverse engineer back during the first moments of their formation, how they actually evolve, interact with the disk, and etc. Okay, so I would like to start with a very standard plot. This is almost all popular exoplanet talks start with this plot. This is basically the distribution of exoplanets that we know today. What we see on the y-axis, do you see my mouse? Yes, I guess. So on the y-axis we have the mass of the planets, and on the x-axis we have the same major axis. This is the distance to their parent star. And just for completeness, I overplot here the planets in the solar system. So we can see here Jupiter is at 1 Jupiter mass, and Earth is at 1 AU, 1 astronomical unit. So there are three distinct colors over here. Obviously, we have the three more successful exoplanet methods for detecting and characterizing exoplanets. That's the transiting method. Basically, we detect passage of the planet in front of the stellar disk, and then we have the Doppler method, which measures the radial velocity of the barycenter of the star, which is actually induced by the gravitational pull of the planets in the system. And we have also the direct imaging method. Basically, that's the first two are indirect methods for detecting planets, and the imaging method is the direct. So basically, we point the telescope and we detect the planets. But these are, of course, only the last one. It's mostly useful only when the planets are very hot and very young, and you can see here that they basically span from 10 to about 80 Jupiter masses. So some of these are actually not the planets, but more like brown dwarfs or low mass stars. So if we just focus over here in the transit and Doppler method, we see that there are a couple of biases that we are all aware. So we tend to find mostly planets which are very close to the star, just because they, that's the easy way to detect them. As we have the strongest signal from transit and from radial velocity when the planet is closer to the star, and we were able to detect these planets first. And of course, thanks to the long-lived Doppler surveys in the last couple of decades, we were able to discover quite a lot of planets which are similar to Jupiter and also much further out. So in a way, we are able to detect already, we start being able to detect planets like Jupiter. But the ultimate question of astronomy, one of the ultimate questions, of course, it's like, what is the frequency of systems like our solar system? How it was formed, and of course, what is the frequency of Earth-like planets? In the sense, in the context of this conference also, we would, of course, like to find more of these. And you see that this is kind of an empty space over here. But I do agree, like with Lars, I'm pretty much sure that there is a lot of planets over here. We just don't have enough precision to detect them, because Earth would only cause 9 centimeter radial velocity, 9 centimeter per second radial velocity signal if it's at 1 AU with the same mass as Earth. So The way to understand how solar system was formed, how it evolved, and what is the frequency of Earth-sized planets, we need to rely on what we have right now. And it's not too bad, because we already know that more of these massive planets, they are not formed where they are. We have, they have probably formed much further out and they migrated. So we already know that there is interactions between the protoplanets with the disk. We know approximately how this physics works. And what is very important is also the multiplanetary systems, okay? Because their dynamics, like I said, it's like it gives you some information how they actually migrate together. So you can do some reverse engineering and you can study some other physical properties like what is the viscosity of the disk, how planets form function of the metallicity of the disk and the star, or also the mass of the disk, and what is the eccentricity and same major axis damping rates, and etc. etc. So why multiplanetary systems are challenging? I mean, let's look at this data. So just don't pay attention. This is no particular system. This is just some random data that I pull out from the archive. I think this is a test multiplanetary system, and to construct the transit model and the radio velocity model isn't that complicated. I mean, I'm not saying it's easy, because it always takes a lot of time for the researchers to get the parameters, but you know, to construct a parameter that you can get the radius of the planet and also the period isn't that difficult. So when you have two planets, basically you have to just put another term and you get the planet. Okay? So basically, just imagine this is another transit further out. And same for the radio velocities. If you just assume that planets orbit in a nearly circular orbit, it's basically like just summing up sinusoidal terms. So it's more or less this is just geometrical models that you can sum up and you get the parameters like from the semi-amplitude of the radio velocity model you get the minimum mass of the planet, and from the depth of the transit you get the radius of the planet. Okay, so let's see what happens if we just publish this system like this, and what happens if we just observe it in the next 2 or 3 years. Okay, so we just applied the same model and something happened. Okay, our model just predicted the transit will be here, but it's actually much later. Or for the planet 2, the transit actually arrived much earlier than we expect. And same for the radio velocities, there is some mismatch. So sometimes no matter what you do, you can try to refit the data, and you might get a good fit here, but somewhere in the middle something is not correct. So the reason for that, of course, it's like, as always, more data, more problems. Don't take more data if you're already convinced in your model. But there is actually physics behind that. I mean, the reason for that, of course, as you can imagine, is that we are actually dealing with the three-body problem. So basically, we have to solve the Newtonian equations, and to model, to base our model on the Newtonian equations, not just summing up Keplerian terms. I mean, this is a cheap way to get the orbital parameters, but in strongly interacting planetary systems, it's not the best way. So if you just apply an M-body model, if you just model the stellar reflex motion around the barycenter, for example, when you have like two planets which mutually interact in a three-body system, you get a model that actually gives you the best orbital parameters. So just want to mention, so here, this is a well-known phenomenon. Maybe you have heard about the transit timing variations. So this is a plot that I took from Eric Ergo in one of, last year he had a talk, and I just asked him for this slide because I really like it. This is the Kepler 8080b, or it's called the king of the TTVs. And on the y-axis you have the time, the transit time, and there you have also time on the x-axis. And basically, if you just observe the transit in one day, and if you know the period, you can always predict when the other transit will come. And this is a linear relation, right? You can imagine. However, if you take the residuals from this linear fit, you get these strong excursions, right? So this is about almost 10 hours semi-amplitude. So basically, the planet is shaking like this, so something is provoking that. And that's, in this case, it's another planet that is not transiting. So from the TTVs, you can actually get sense of other planets which are in the system, but are not really transiting. And there are different origins of the TTVs. So the most simple one are, let's say, that the The two-body TTVs, well, not simple, but well, it's not involving another body to perturb the system. So this could be tidal effects between the star and the planet, or actually, if the planet is much closer to the star and it's also eccentric, you might get this general relativity precession. For instance, if another alien civilization observes the Sun and it sees Mercury in transiting, we know that due to the gravitational, the general relativity, the Mercury will start precessing and they will observe TTVs. Okay? This is not TTVs thanks to another planet is pulling the planet, but it's basically general relativity. What we will refer today is basically the n-body TTVs. So these are thanks to the planet-planet interactions, and they depend on many things like mass ratio of the planets, also the orbital period and eccentricities, of course. And they are very strongest near the mean motion resonance, in particular in their conjunctions. So just to understand what approximately is going on, if we have two planets and they orbit around the common mass center, and for example, S1, satellite 1 is making one orbit, whereas the satellite 2 is making two orbits. They are in 2-to-1 resonance, but they always meet almost the same time. And when they do, they exchange orbital energy and momentum. So basically, when the satellite 2 is giving some energy, it decreases its orbit, or actually, in this case, it gives some energy, and the orbit is expanded. So that's particularly the orbit slows down, so the transit will occur a little later, and in the next conjunction actually will give some or will receive some energy, and the orbit will speed up. So basically, they are always anti-correlated. So when one speeds up, the other slows down, and etc. And this is how it actually looks if you just take test data. This is a TOI test object of interest 2525. This is how many objects of interest we have even more now. And you can see these so-called river plots. So if you take transit data, you see that how the transit actually follows these river-like shapes. And one way to model this, of course, is to apply a full photodynamical model, just like Veselin presented before. Well, he was more interested about binaries with planets, but here it's still a three-body problem. So basically, we have one central body and two planets, and you can model the shape of the transit curve, taking into account the dynamics. But one easy way you can approximate that is if you take, let's say, if you model only the time of mid-transit, and you can do, let's say, TTV modeling. So this is exactly what I did in this paper, because the photodynamical model was just far too expensive. So what we did is we just take the mid times and we model it with an embodied model. And in the bottom you see that we also obtain some radio velocities which are fully consistent with our analysis. Well, the problem is that that was during the COVID crisis, so most of the facilities were closed, so we were not able to take too many radio velocities, but you can see that they are from PFS and Ferrous data are very consistent. And you can see here when one of the planets is actually arriving earlier, the other is getting later, and etc. So this is in off-phase fashion. And what about the radio velocity case? Well, we discovered this dynamical perturbation first on the radio velocity systems, and this is the system GJ876. This is the Rosetta Stone for all planetary dynamics. I mean, it's very well studied system. So it consists of an M-dwarf which hosts two Jovian mass planets with 30 days orbit and 60 days orbit. So basically they're in 2-to-1 resonance. And you can see here on the right plot, this animation, you can see that the time scales of their dynamical interaction is very short. Yeah, they're about 10 years. So this is really observable, and the precession actually it's coming over here on top of the radio velocity signal, and this basically it's not thanks to another planet. This is basically the precession of the orbit. And what is important for the mid-motion resonances, there are at least, I mean, I don't want to go to details, but there are some important resonance angles which must vibrate around a certain value in order to the system to be in resonance. It's not just necessary to have system that is in close to 2-to-1 ratio or 3-to-1. For example, Neptune and Uranus, they have a period ratio close to 2-to-1, but they're not in resonance. So you need to have a specific dynamical behavior to call it a resonance. And yeah, this just want to introduce, this is data from HIRES. Harps and Carmenes, and this is just a recycled plot from my paper in 2018, but we have far more excellent Carmenes radio velocities over here, which will be published soon. Okay, so I just want to introduce another system, and this is more or less why I think it's very important to apply dynamical models. Just want to mention here that here Keplerian model is not even possible to fit. Okay, you always have to apply a dynamical model. Keplerian model doesn't work. So here Keplerian model works in this system. You can model this data very well. This is data-set system, which is my first planet discovery ever, and I was very happy because this is where exactly the first time I applied dynamical model, and I realized that if you apply Keplerian model, the system is unstable. You can get the parameters, right? But if you apply dynamical model, not only you get the better fit, but actually the system is stable. Okay? And now look at the periods now. We have the inner planet with 407-day period and the outer of 740-day period. So this is not 2 to 1, right? This is like 1.85 or 1.8, something like this. So let's see what happens when the system forward in time and see what happens. Alright, so we started somewhere here, which is period ratio below 2. But when we integrate the best orbital parameters from the dynamical model, we get a resonant system. Okay? So if you take the mean period ratio over here on this plot, you see that it's actually 2. And all the resonance angles I'm not showing over here, but they are liberating, and the system is perfectly fine in resonance. And now the interesting thing is that we can actually do some reverse engineering, because this is a very specific system. You cannot get it with any channel. There's only one channel that you can get this particular configuration. So there are different approaches. You can either integrate backwards, or you just try different parameters and you run more sophisticated n-body simulations. For example, we can try to we can put two bodies and just simulate that they are actually migrating in a disk, and at some point their period ratio will cross 2 and they will be locked in this 2-to-1 resonance, and they will continue to migrate inwards in a resonance. And we can actually precisely get, well, here at some point they will start liberating in the same configuration, which is the main idea why we should always apply dynamical model source. Just a brief slide over here. This is just a subsample of the more massive planets which are found around more massive stars, the intermediate mass stars from radio velocities. And on the y-axis in both plots is the stellar mass estimate, and here this dashed blue line is the so-called ice line or snow line. So here in the protoplanetary disk inside here we have enough solids and enough gas and enough ice to form our giants. So most likely all these planets that we find over here, they have been formed much further out and migrate inwards. And you can see some characteristic mean motion resonance ratios that they've been formed. So we have like 6-to-1, 4-to-1, 3-to-1, and let's say first order resonance like 4-to-3. But there is a bunch of pairs over here which are actually outside of the 2-to-1. But one of them is actually aesthetic because, like I said, the best fit parameters are not pointing to 2-to-1 resonance, but when you integrate, it's actually going to the 2-to-1 resonance. So what is important? This is a very serious bias in exoplanet archives. For example, you take you go to, let's say, Exoplanet AU or the NASA catalog, and you just retrieve the data from there, what is published, and you try, for example, scores are trying to reproduce these systems. And that's because they are actually quoting the nominal best fit parameters, but what is important is the dynamical parameters, the oscillating parameters. Okay? So, therefore, if you try to reproduce these systems, you might fail, or you might reproduce them, but they will probably not be what actually you observe. So you have to work with the dynamical parameters over here. And this is what we want to do here in Sofia University. I started a group thanks to a grant called Vihren, which is funded by the Bulgarian National Science Foundation. And it's called Exoplanetary Dynamics and Stability, Reverse Engineering of Stable Multiplanetary Architectures. And this is my team. Please go and talk to them if you want to learn more about us. This is Vladi, Desi, Milen, and Denica. They sit over there. Please talk to them if you want to learn more about us. Another thing I would like to point out is that we are also developing a software which can combine all these dynamical models, Keplerian models. You can do Bayesian or frequentistic analysis. You can do mean motion resonance analysis and fit transit radio velocity data, and even recently we included also astrometric measurements. So you can see here it's very easy to detect multiplanetary systems if you have all the data. And by the way, in the ExoStriker we have included more than 350,000 unique radio velocity measurements. Okay, so you have more than 6,000 stars to do some data mining and find exoplanets. And I know groups that did that. So basically they have found planets using the ExoStriker data. So it's all available in the GitHub, and I would urge especially younger scientists to try it out, because you'll see that it's very intuitive and very fast to learn. And also you can do some serious science with it. And now basically this is it what I wanted to tell you, but I said that I would like to show you something new. Do I have time? I'm sorry, I didn't measure.
Yeah, a few minutes.
Okay, a few minutes is fine. So I would like to show you a very fresh test example. Okay. So this was a single transit system. Okay, I think it was like test sector 31 or something like this. And I'm part of one group called the Wine Survey. It's basically warm giants we test. And this is joint collaboration between a number of German scientists and also a number of Chilean scientists. So what we do actually is we are scanning the test data frames, and we are trying to find out basically more massive planets and try to characterize them with the follow-up observations from ground, from Doppler surveys. So basically we try to complement the orbital parameters of the test light curves and to validate these planets. But this one, it's only one transit. So one transit is not giving you much, right? Although by the duration of the transit you can guess the orbital period using the Keplerian law, but one transit is okay. It gives you a hint that there is a planet. So good that we have some data from Pharos and Harp, so we apply for time regularly and we get radio velocity time for this system, and this is where we actually end up. And a colleague of mine said, you know, we gather enough radio velocity, so let's look at the models. And they sent me the model and said, okay, we actually have two planets. One is with 76 days, which is transiting one, and the other is with 350 days. And they're both very eccentric, and you can see that they're also very massive, about 7 and 9 Jupiter masses. But you know, I work with radio velocities more than 12 years already, and I have a keen eye. You know, I said like, no, this model will not work. No. And I said like, I also have a like n-mode integrator in my head, and I said, like, okay, this will not be stable either. You know, this is not the right model. Second, it's not going to be stable. So I tried to experiment a little bit, and also together with our group in Sofia 2 weeks ago, we actually, I just wanted to say, yes, it's not stable. I forgot about this slide. You can see the configuration, you can see the planet, the inner planet is ejected only within 500 years. Okay, I just want to mention that it's not working. So we end up with a better model, far better model, which is in 2:1 period ratio. Okay, so if you take this data and you model them dynamically, and you get a much better configuration. And I called these guys in Chile and said, like, look guys, please take some more data, because I think it's worth it to see whether that model works. And they take a few more data points from Harps and Pharos. So basically, blue is Pharos, if I didn't mention, sorry, red is Harps. And they get some more data points, and actually the data points arrive exactly where we predicted. Okay? And now, this system is perfectly fine, perfectly stable, and in 2:1 mid-motion resonance. Okay, so if I would let my colleagues to apply their Keplerian model, it might actually end up in the literature with a wrong period and wrong dynamics. And of course, that's a major bias to the community, because we want to have the most accurate configuration, and we want to know the dynamics, and we want to understand how that was formed. So these kind of systems are very important, because we can after that try to reproduce precisely their dynamics and see how planets interacted with other planets and with the disk, and get some physics out of it. So from the data, from the exoplanet data to the theory, we are basically providing a direct link between these two. And basically that's what I wanted to say, and thank you very much for your time.
Bulgaria from Institute of Astronomy, Bulgarian Academy. I would like to ask you, what can we expect from the migration of large mass planets as an inflation of the evolution of Earth-like planets in the system?
Well, there are a number of studies in this direction, and you know, there are different channels. So basically, you're asking me how. Let me see if I understand. So you're asking me what we would expect for Earth-like planets in the influence of more massive planets migrating together. Well, I think what we find out is that in case they are, of course, there's stability involved, of course. If the more massive planets migrate much further in, there will be no Earth-like planets. They will be all smeared down and they will be kicked out or engulfed. So that's why I think what we would like to find out is like a Jupiter-sized planets. Okay, so therefore there's a better chance to get planets like Earth in about 1 AU. I mean, if one planet migrated from further out all the way to the hot Jupiter phase, basically there's not much to see there because of stability. Of course, hot Jupiters are relatively rare. They're about 1% of all the exoplanet systems, so there's still quite a lot of room for Earth-like planets to survive this kind of migration. Also planet-planet scattering and different resonance evolution that might happen in the system. But overall, I think it's quite chaotic, and we need to. There are of course some common patterns and common physics, but we have to understand that it's like it's probably very chaotic, the whole process.
Thank you. Rosita Bogotaniko, Bulgaria. You said that the long-term goal is to understand systems with multiple planets and to study them. And I'm wondering, what is currently the outlook? How many systems are we aiming for to get in the next decade, 2 decades? What questions do we hope to be able to answer?
So the radio velocity service keeps going on. Okay, and by going on, we will start recovering some of this empty region over here. I suspect, yeah. So we're trying to fill out this gap over here, and that can happen only by long-term radio velocity surveys. So surveys like HARPS, they should never stop, right? We should not upgrade this instrument nor take it out. We should keep going on, I think. Well, I think by taking more and more data, we start recovering more and more massive planets like Saturn and Jupiter. I think has basically no chance to recover these kind of systems like Uranus and Neptune, because they have just a small signal. And we might, well, let's see if the second Earth initiative and HARPS-3 are operating in the next couple of decades. We might actually try to operate also this region over here, right, where we actually aim. The purpose of our program here, ExoStar, is actually to look in the archival data, because I am convinced that there are a lot of systems that need to be redone, not only with new dynamical models, but also with new data. And this data actually exists in the archives. So we were trying to get and do one systematic search from A to Z, from all the multiplanetary systems, and of course try to discover new planets. Maybe we'll add a couple of here. But of course, we try to give better understanding of the orbital parameters and how many of these are actually resonant, because I'm pretty sure some of them are actually missed by previous groups. Not because they were lazy or something, because this was just the way how it was doing it. I mean, some of these multiplanetary systems, they've been discovered like 10 to 20 years ago, and nobody bothered to revisit them. And now. But now we have better computers, more CPUs. We can do, I would say, more complete work. So that's what we aim here. And the future will show, what the new surveys and the follow-up surveys will bring us.
Okay. Well, I think last question for the call.
Yeah. I'm interested in process. Because much of what we're seeing here is descriptive, but there's so much to unpack, even in a figure such as this one. In our own solar system, people who carry out n-body simulations for planet formation, which we're going to hear a lot more about as the workshop progresses, seem to show that the terrestrials form in the inner solar system of around their host star by canonical accretion, as opposed to how you form gas giants at or beyond a snow line by gravitational instability, pebble accretion, etc. These are two fundamentally different processes that lead to ultimately different planets. Insistent, and so here's the naive one, because you know the statistics, people in this room better than anybody. When giant planet migration occurs, type 1 probably, it's going to drive into the inner solar systems, and three things are going to happen to those terrestrial planets in the way. They'll be plowed and gobbled by the giants. They'll be tossed out of the solar system or go into the star, which I think is the least likely of those. Does that mean that observations show that in these close-in giant planet systems, that they're top-heavy, like this? Because I don't see how you can escape a situation where you have only giants close in and no straggler terrestrials farther out.
Okay, so let's see. You're saying that there might be actually, for one of these systems, that the giant actually migrated all the way into the hot Jupiter or warm Jupiter.
It's hard to make the giant planets close to the star.
No, yes. I think there is a common consensus among scientists that actually they migrated, right? So there are some studies that they predict that you can form them in situ, but it's yeah.
But in observation, do you ever see smaller worlds outboard?
I'm not aware, to be frank. I mean, if there is a Jupiter, if there is a hot Jupiter, basically there is no, at least I'm not aware of evidence of Earth-like planets further out. Or let's say it's not Neptune. There might be some peculiar systems. I think there are, let's say, a Jupiter-sized planet and a Neptune-sized behind. Okay, that's doable.
Mm-hmm.
But I don't think we have the precision to find Earth-like planets when you have also Jupiter-mass planets. This is also kind of challenging. So we have from tests, at least, for example, many systems that we have found, let's say, these kind of warm Jupiters, warm giants. When we measure the masses with radio velocities, we find out that the inner planet is far more massive. It's like Jupiter size, but the outer one, it's like a Neptune-sized planet. But I'm not aware of rocky planets being behind the hot Jupiter, for example. So, and that's the dynamics actually. I think it will just take them out from the system, as you say. Yeah.
Okay. Anyway, I think we need to have a coffee break. I think we're going to try to go for a 15-minute coffee break,
Okay.
And then we'll return back here for our concluding talk.
Okay.